Solubility equilibria involve the dissolution or precipitation of insoluble salts. You might have learned in earlier chemistry lessons that many salts are soluble and others are insoluble. Well, what we're telling you today is that insoluble salts are actually a wee little bit soluble. In other words, there's no such thing as a salt in a solution and in the solution there exist no ions of that salt. There are always some. Now, it might not be very many, and we call those salts insoluble, but there are always a few, and that's what we're dealing with here. For example, here are some insoluble salts: barium sulfate, silver chloride, zinc carbonate, lead 4 sulfide. If you would like to review the mnemonics for soluble and insoluble substances, the mnemonics that I came up with, see the lessons in the unit on solutions. I think they're the first couple of lessons in that unit. But all of these, my students have learned already that these are insoluble salts. And what we're saying today is that they're actually just a wee tiny little bit soluble. Let's consider a saturated solution of a typical insoluble. Here are a couple of patterns that might exist. Mn, M stands for metal, N stands for nonmetal. We could write cation and anion, but M and N are nice and short and convenient. This first equation might apply for something like the silver chloride that I'm circling here near the top of the screen. The ratio of ions is 1 to 1. Actually, that equation would also apply for the barium sulfate, where the barium ion and the sulfate ion are in a 1 to 1 ratio. Similarly, zinc carbonate, those are in a 1 to 1 ratio. So the first three insolubles that I've listed here would basically conform to the top equation. The bottom equation, you can see that the ratio of cations to anions, or metal ions to nonmetal ions, is 1 to 2. That would be similar to this lead 4 sulfide compound that I've listed here at the top, etc. Okay, you have to look at the formula for your insoluble and you simply break it into its ions. For these cases, the solubility product constant, KSP, is equal to these expressions here. Remember that an equilibrium constant is always products divided by reactants, and we raise each substance to the power of its coefficient in the equation. KSP expressions never have denominators, and that's because the reactant is a solid, and we don't write solids or liquids in K expressions. Any KSP expression will never have a denominator. KSP is the equilibrium constant between undissolved and dissolved ionic solute in a saturated aqueous solution of an insoluble. In the upper right corner of the screen here, I've tried to indicate what's going on. We have the solid bit of the salt that we could see if it were in a beaker, and then we have the ions that we can't see because they are aqueous, dissolved in water, and there's an equilibrium between these two things. There's a constant exchange of ions. At any instant, some ions are dissolving out from the solid form into the aqueous form, and at the same rate, some of these ions are crystallizing into the solid form. So in real life, down in the lower right, I've shown a picture here. I'm not sure what compound we're dealing with here, perhaps silver chloride, but in any case, there is going on here, which we can't see, the constant interchange of ions from the solid form to the aqueous form, and from the aqueous form to the crystallized solid form. It's at equilibrium, so those rates are equal. A compound that has a small KSP, not much dissolves. A compound with a large KSP, quite a bit dissolves. And I put quite a bit in quotes because, by definition, any compound that has a KSP is, quote, insoluble, unquote. So an insoluble compound certainly isn't going to have much in terms of ions floating around. But the larger the KSP value, the more ions there are in the solution of this insoluble. Let's try one. Let's write the solubility product constant expression for lead 2 chloride. We need to write the formula for lead 2 chloride. We would write it dissociating, which it doesn't do very much of because it's an insoluble. But the bit that does dissolve dissolves in this way that I've shown here, forming a lead 2 ion and 2 chloride ions. Well, the KSP then is simply Pb2 plus concentration to the first power and Cl minus concentration to the second power. Let's summarize solubility equilibria in the KSP. In this lesson, we introduced the idea that, in reality, all insoluble salts are actually slightly soluble. Some are very slightly soluble, but all are soluble. The solubility product constant, KSP, sometimes just called the solubility product, is the equilibrium constant between the undissolved solute and the not very many dissolved ions. KSP expressions have no denominator. The reactant is the undissolved, i.e. solid, solute. Reactants go in denominators, and we don't write formulas of solids or liquids in equilibrium constant expressions.